Good Friday evening. Good time to do number theory. I'm going to go over Monday's lecture so that you can watch it online and get ready for the exam early if you need to. I'm downloading Maple, so it's taking up a lot of space. So, like my stamp for Fermat, this is Pierre de Fermat right up here, and this is Fermat's last theorem, and down here at the bottom is his actual notes about the theorem, which we're going to actually talk about pretty soon. So I want to first talk about this theorem, which is not Fermat's last theorem, but that if A and M are relatively prime and A has order T mod M, just to remind you, order means that it's the minimal integer, positive integer T, such that A to the T is congruent to 1 mod M. Then T has to divide the totient function of M. So how can I use this? Well, I can answer questions like, what order can an integer have mod n? By the previous theorem, if m is 9, then phi of 9 is 6. We've already cranked this. You've cranked it for homework. And the order has to divide phi of 9. So the possibilities are 1, 2, 3, or 6. So exam questions like this will appear, where what are the possible integer possibilities for the order, and what you would do is calculate the totient function and then write down the possible orders, and then maybe even test out whether they indeed are the order. Here's another theorem. If P and Q are odd primes and Q divides A to the P minus 1, realize that this is a redefinition of A to the P is congruent to 1 mod Q, then either Q has to divide A minus 1 or Q is equal to 2kP plus 1 for some integer k. I'm going to prove this one for you. I'm not going to put it on the test, but I just want to prove it for you. Like I started out earlier, since Q divides A to the P minus 1, we know by definition of congruence that that's the same thing as A to the P being congruent 1 mod Q. Then the previous theorem, the one that I presented for you last Wednesday, implies that T has to divide P. T is the order of A. But then T is 1 or P because P is prime. But if T is 1, then A is congruent to 1 mod Q, or Q has to divide A minus 1. Recall that in the theorem, this is one of the possibilities. The other possibility is T is P. Well, T is P, then P has to divide the totient function of Q by the previous theorem, but the totient function of Q is equal to Q minus 1, which we calculated by hand because Q is prime. So that means P has to divide Q minus 1, or Q minus 1 is R times P for some integer R. But since Q is odd, Q minus 1 is even, so that means R times P must be even. But P is odd, so that leaves only one possibility, that R is even. So R must be 2 times K for some K. So how do I use this? Well, here's an example of how I can use this. If I have a divisor of 2 to the P minus 1, where P is prime, it must be of the form 2kP plus 1. So I'll put a problem like this. For example, what is the smallest possible prime divisor of 2 to the 19th minus 1? Well, all the divisors are of the form 2kP plus 1, where P is 19. That's from the corollary in the previous theorem. 2 to the 19 minus 1 is equal to 524,287. So if I make a table, the first possible prime divisor turns out to be 191. It actually doesn't work. I just tested whether 191 divides 2 to the 19 minus 1, and it does not. If we have two integers a and m and we expand them via division algorithm, r is the least residue. So this is the way of only looking at congruence classes that are up to the number that I'm thinking of, like m. So if a is the least residue and the order of a is phi of m mod m, then a is called a primitive root of m. I'm going to make another module with this definition so that it's separated from this previous module.